I'm making this video in response to a student question I received recently. Here's the question. I have a question about the mammogram example. Why are the 10% false positive taken out of the complete 38 million sample, which includes positive and negative results? In other words, how can a negative test result be false positive? Thus, of the 38 million women who get mammograms, 10% or 3,800,000 have false positives. Okay. Now, here is the section. This problem's coming out of the Bayesian flip article. And this is the section of the article that's relevant for the probability calculation. Every year in the United States, 38 million women are tested for breast cancer with mammograms. Of these, 140,000 have cancer. Mammograms have been determined to be 90% accurate for women with breast cancer. This figure was calculated by tallying all of the women who were eventually determined to have breast cancer and looking back to see if their initial mammograms were positive. Thus, we have the probability of a positive mammogram given cancer is 90%. In using a similar empirical investigation, and here empirical means using data rather than like theoretical or hypothetical mathematical kinds of models, but using a similar empirical investigation, we found the probability of a positive mammogram given no cancer is 10%. That would be the false positive rate. Now that those two numbers add up to 1 is just a consequence. When they refer to them not in general being complementary, what they're referring to as the complement rule. It is important to know that a test is both powerful and has a relatively low rate of false positives. But when one is faced with a positive mammogram result, these are hardly useful. We administer a mammogram because we do not know whether or not someone has cancer. What we want to know is, what is the probability of cancer given mammogram? So this is a really, this example, to me, it ties right to the definition of p-value. And this idea of the Bayesian flip is switching between what's assumed and what's not being assumed. So there's a difference between the probability of getting the data that we're analyzing given the null hypothesis is true. That's the definition of p-value. But what we're actually interested in is the probability the null hypothesis is true given the data we've collected. And that second one is the one that we really don't have any good way to calculate. In this situation, though, we can calculate the probability of having cancer given a positive mammogram. And we see down here that the book or the article in the calculation in the article that's coming out to be 3.6%. So it turns out not very many people who get a positive on a mammogram end up having cancer. The one thing what I realized, it's interesting, when I started to work through this problem and figure out how to come up with an explanation, one of my go-to methods is always using a tree diagram. I like using tree diagrams. Seeing the numbers visually helps me understand. And so I thought, well, I'll create a tree diagram here for this situation. And through the process of doing that, what I realized is their calculations in the article are not correct here. First of all, let's take a look at the necessary information that we're given. We're told that 140,000 of these the patients have cancer. And to me, what that means is, what this implies is that 37,860,000 patients do not have cancer. And this is important to me because this will be the first branch of the tree I'm going to create. And here we have the other given probabilities. Probability of a positive mammogram given cancer, probability of a positive mammogram given no cancer. So when I create a tree diagram, this is the type of thing that I'm looking at. Now, usually in my tree diagrams, I'd have probabilities here, decimal numbers. But the book, or the article's methodology for doing this calculation was to look at counts, which is actually, in this case, it's a pretty nice application. A lot of times when we're using tree diagrams, we don't have the total, like 38 million, to work from, so we can't do the calculations in the same way. So as I start thinking about how to do this calculation, and the calculation that we're going to do here is the probability of cancer given a positive result, what I like to do, whenever I think about probability, or one of the ideas that I have in my mind is this idea that we're going to look at, in the numerator, an event, and in the denominator, we're going to look at all possible events, the probabilities of all possible, or the numbers of ways each of those events might happen, and all the possible events. Now this, given that, okay, the vertical line means given that, or such that, given that the test result was positive, means that we're only going to look at these two branches of the tree. Because we don't need to look at the negatives, or we shouldn't look at the negatives, and the reason is because we know the test was positive. So we know that 126,000 plus 3,786,000 patients got positive mammograms. Now, of those, 126,000 both had cancer and a positive result. And this is where we're differing with what the calculations in the article came up with. Now I'm just going to go ahead and use my calculator here to add up this denominator. I could probably do that in my head, but the problem is, too often when I try to do these kinds of calculations in my head, I make mistakes. So I just think I'll go ahead and do it on the calculator. So here the denominator becomes 3,912,000. And let's see, so that would be one. I'll finish this calculation here. So I'm getting about 3.2% instead of 3.6%. And really that the reason this is occurring is because I'm splitting that 140 with cancer. I'm splitting off the false negatives. So it's really bad if you get a negative result and you actually have cancer. And actually, I think it's worth even doing that calculation. So what is the probability given this is the worst thing that can happen. A patient that gets a negative on their mammogram and they actually have breast cancer. And the reason that's such a really bad thing is because they won't get treatment. Why would they? They think they're fine. And so this calculation, we would have the probability of, or the proportion of the population, in this case I'm looking at counts. This is the people who have cancer and also got a negative. That's the 14,000. And then I'm going to look at of all the people who got negative results in the denominator. And we can already see this is a really big denominator. This probability is going to be really small. Oops, let's see. I use some parentheses this time and do the whole calculation in one step. So with this works out to about we got tens, hundreds, thousands, 10,000. So about 4 patients out of 10,000 tested will end up with having cancer or get a false negative. And what is that? That's like 1 out of every 2,500 patients. And in fact, whenever doctors or whenever clinicians are designing these diagnostic tests, this is the number they want to be very small. I mean, if you get a positive on your mammogram, if a woman gets a positive on their mammogram, you should remember that there's a low chance that they actually have cancer. But what it does mean is they will go and get more diagnostic work done to find out for sure. So anyway, I hope this video helps clarify your understanding for this part of the Bayesian flip article. And remember, you can always message me questions. I really like getting your questions and responding to them.